We're going to look now at an electrical example of a damped driven oscillator. That is the RLC circuit, a circuit with a resistor, inductor, and capacitor driven by a sinusoidally oscillating voltage. What we have to do first is find the voltage across each of these three components. We'll start with the capacitor. The voltage across a capacitor is Q, the charge in the capacitor, divided by C, the capacitance. Next, the voltage across the resistor, we can use Ohm's law. V equals I, R. I is the current, R is the resistance. The current now is the rate of change of charge. It's coulombs per second. So I is dq dt. In other words, we can write VR, the voltage across the resistor, is R Q dot. Q is the dot is the time derivative of the charge. Next, the voltage across the inductor. That is VL equals L, the inductance, multiplied by the rate of change of current. But remember, the current is the rate of change of charge, so this term here is actually Q double dot. So we can write VL is equal to L Q double dot. And all these three terms, VL, VR, and VC, they must be equal to the driving voltage. So we have VL plus VR plus VC equals the drive. In other words, we have this equation here. And you see this has the same terms that we've seen before in damped driven oscillators. Second derivative, first derivative, zeroth derivative, and a driving term. Writing gamma as R on L and omega naught squared is 1 on LC, we find an equation in very familiar form. And we know the solution to this. Using results from the previous videos, we can say the steady state response of Q is given by the drive multiplied by this term here. So now we have an equation that relates charge and voltage, but it would be nice to have an equation that relates current and voltage because that's normally what we think about in circuits. The current, remember, is the time derivative of Q. Now Q has the time-dependent part as e to the I omega t. There's no other time-dependent part. So the time derivative of Q will just give us a factor of I omega out the front and then the function of Q back again. So in other words, the time derivative of Q is equal to I omega Q. And so we can write a little rule that every time we see a dot, we take the dot away and put a factor of I omega out the front. So we can apply this rule with the derivatives to our equation. So every time we see a dot, we've got to take an I omega out the front to get rid of this derivative. So with a double dot, we get two factors of I omega out the front. With a single dot, we get a single factor of I omega, and that's the end of our rule. So now we've got this equation where we've taken these derivatives explicitly using this form of Q, which we have from the steady state solution of our equation. So next we can rearrange a little bit, replacing I omega Q, that is I omega Q here, with the current. So we lose a factor of I omega here and replace it with the current, and here we just have the current by itself. And here, to get the current, we can divide by I omega and multiply by I omega to change the charge Q into the current. So now we've got an equation with voltage and current. We can rearrange this to find the voltage equals the current times something. Now you're familiar probably with Ohm's law, where V equals the current times the resistance. Well, this is a generalized Ohm's law that includes the effect of inductors L and capacitors C and the resistor R. So if you take the inductor and the capacitor away, that would mean making L to 0 and the capacitor taking that to infinity, then you just get the normal Ohm's law. But now we have this generalized thing here we call impedance, and the complex electrical impedance ZE is given by this equation here that includes terms for the inductance and the capacitance. And the thing that they introduced that is really interesting is a phase shift. So if you have an inductor or capacitor in your circuit and you're driving it with some alternating voltage, some AC voltage, then the phase of the current is going to be different to the phase of the voltage because these inductors and capacitors give you a phase shift between these quantities. We're now going to look at the analogy between the electrical and mechanical oscillators. This is the equation we just had for the electrical oscillator, the solution for the charge in terms of inductance, capacitance, and resistance, the solution for the voltage in terms of the current and complex electrical impedance, which we defined to be this. So we've got some rate gamma, which we've written in terms of resistance and inductance, and omega naught squared in terms of 1 on LC. When we look at the mechanical system, we have an equation relating force and mass and position and spring constant and damping rate. We solve for the position in terms of those quantities like this, but we didn't write down an analogous equation to this voltage current equation that we have here. When we think about this, then here the current is the rate of change of Q. The analogous quantity over here would be the rate of change of X. So actually what we're looking for is some equation that relates force and velocity. We can do it by analogy. We can write force is equal to the velocity, which is x dot, times Zm, which is now the mechanical impedance, and we can define it like this. So we can define the complex mechanical impedance to be the damping rate, I omega times the mass, minus I times spring constant divided by the frequency, or we can write it in pretty much the same form as this equation here by making factors of gamma and omega naught squared, where gamma is R on M and omega naught squared is K on M. And what we see, in fact, is that there are substitutions we can make to convert between electrical and mechanical oscillators. The inductance behaves like the mass. For example, here we have inductance here L, over here we have the mass. The resistance in the electrical circuit looks like the damping rate in the mechanical system. The spring constant K looks like the inverse of the capacitance. So see, for example, here we have 1 on C, but here we have K in the numerator, and the voltage is analogous to the driving, F. We're now going to look at a collection of different phases. So remember I said that the action of a capacitor and inductor is to introduce a phase shift between the voltage and the current. For a mechanical system, the spring constant and the mass introduce a phase shift between the force and the position. So let's think about the mechanical system again. So this is the equation of motion for the mechanical system. And we found the steady state response previously, xp, is given by all of this. Now I can write the denominator here in terms of the complex mechanical impedance, which was given by this. I'm just taking out a factor of omega. This allows me to write xp in terms of the mechanical impedance, and it looks a little neater. I've got a factor of I on the bottom here. I can take that out and write it as e to the negative I pi on 2, so I've got rid of this factor of I. This Zm, though, is a complex number as well, so I can take the absolute values here and put another phase on the top of this expression here, e to the I theta. So in other words, theta is the argument of the inverse of the mechanical impedance, or negative the argument of Zm. But you may remember previously, when we solved for xp, we expressed things in terms of an angle phi. Maybe you don't remember phi, because previously we had xp is equal to a e to the I phi e to the I omega t. So phi was the angle between the position and the drive, and a is the amplitude of the position. And we had expressions for the phase phi and the amplitude a. So what's the relationship between phi and theta? Well, we look at this expression here for xp, and what we see is that xp is equal to some real valued number here, so that must be a. So a is f naught on omega, the absolute value of Zm. And the angle here between xp and the drive is e to the I theta minus pi on 2. So phi must be equal to theta minus pi on 2. So we can write phi in terms of theta and vice versa. So in summary, phi is the angle between the drive and the position of the oscillator. Theta is the negative of the phase of the impedance, and theta is equal to phi plus pi on 2. This is an awful lot of bother to derive an extra angle theta when we already had a perfectly good angle phi. But we will see shortly why this angle theta means something and why we bothered.